Okay, so we're looking to sketch the graph of this function. Let's ask a few questions to begin with. What is the degree of the function? Oops, let me get my pen. What is the degree of f? 3. How can we tell that?
Because we see two x's, however, one bracket has a multiplicity of 2.
Nice word. I like the word multiplicity. So this one has a multiplicity of 2. We've got a linear factor here with a multiplicity of 1. We can see that if we were to expand this, the degree is going to be 3. What is the lead coefficient?
2.
No.
2x.
Oh, sorry. 2. 2. The lead coefficient is 2. What is the y-intercept constant? Can we see the y without expanding? Can we see it?
Yeah. You can just -4.
What's it going to be?
-16. 7.
-16.
Plug in 0.
Yeah.
Plug in 0. We have 2 squared, which is 4. Times 2 is 8. Minus 1. -8. How is it -8?
Yeah. Put in 0.
Which fools want to go for -8? Hands up.
How is it -8? Why did you plug in 0?
-8.
Yes. Because you get 2 squared, which is 4. 2 times 4 is 8. And then that's -1. 8 minus 8.
How do you get that? 2 times 4 is 8.
It's just
2 squared, 2 squared times 2 is 8. You go by
times
-1.
I sense a bunch of people who've missed a little math lesson for a while. Oh, man, we can talk about math. Okay, all right. So this information basically lets us almost sketch it. What are the x-intercepts?
-2 twice.
Let me,
-2 twice and -1. Twice, yeah, twice.
-2 and 1.
Yeah, no, like that means you're gonna touch it and go up. Yeah, if there's 1, it's gonna go through. So it matters.
I didn't know that.
no, because there's no x outside. That 2 doesn't have an x with it, so it's not going to give us a root there at 0. So we are going to go through this point at -8. We're going to go through here at -2. We're going to go through here at 1. What's the end behavior?
Approach infinity on both sides. And minus. Wait, no, it doesn't go down -8. As x approaches infinity, y approaches -infinity. Oh no, it's negative infinity.
Yeah, it's negative.
Negative. No. Because look on the left side, like this. Look at this. Oh, when x goes to infinity. Oh, it's just infinity negative.
Okay, so this is third degree. This is a third degree function. So when you get to infinity, the function basically acts like this function would act. All the other bits and pieces don't matter when you start getting big numbers. The cubing takes over, it has so much more power than the other parts of the function. It acts and operates like this one. So as we go towards infinity, y will go towards infinity, and as we go towards negative infinity, y will go towards negative infinity, which means it's sort of going to enter in these directions like this. So anything else we can do to sketch it? So if we're coming from here and we've got to go through there, we can sort of see that the function's going to look like this. The function's going to look like this. How do we know that? Well, in brief, that you've only got 3 types of possible functions. So A linear function is going to look like this. So the end behaviors are going to be. So let me do it like this. Ooh, somebody's alarm's going off. So your function is either going to have n behaviors that look like this. We do one more of these. For a polynomial function, your n behaviors are either going to be like this, like this, like this, like this. You have these sort of combinations. So this one is an odd degree and positive. This one has an odd degree and negative. This one has an even degree and negative. This one has an even degree and positive. So your n behavior for a polynomial function is going to be one of these four. This one's got an odd degree and it's a positive leading coefficient. So if it's odd degree and positive leading coefficient, odd degree and negative leading coefficient, even degree and negative leading coefficient, even degree and positive leading coefficient. You would have these n behaviors. If you have a root which has a multiplicity of 1, it's going to have a change of sign. It's going to create a change of sign here, which means it goes through this. If you have a root which has a multiplicity of 2, it's going to have no change of sign, because that factor, this factor here, cannot change the sign. Whether it flips from either side of -2, the result of that is still going to be positive. This cannot create a change of sign. The only thing that can cause a change of sign, so this factor here, when x is less than 1, is going to be a negative. When x is greater than 1, it's going to be a positive. So it creates a change of sign. So this will change the sign. It won't necessarily make it go from negative to positive, depending on where it was caused by all the previous ones, but it will cause a change of sign. So as you go either side of the 1, the sign will change. So the sign of the whole function will change. This one is always going to be positive. It's not going to create a change of sign. So to go from one side of the axis to the other, you have to have a change of sign occur, and it's caused by the root. A square factor, if the exponent is even, it will never cause a change of sign. It will always give you this sort of turning point. If the multiplicity is odd, it will allow a change of sign. If the multiplicity is even, it doesn't allow a change of sign. It's always positive. If the multiplicity is odd, it will create a change of sign, which means it will cut through the x-axis. And it cuts through the x-axis in various ways. You've got three basic things depending on the multiplicity. So a root can cause three possible sort of shapes. So if the multiplicity of the factor of the root is 1, it's going to go through like this or like that. So if it's 1, it's like this. If it is even, it's going to do one of these. If it's even, it's going to do one of these two. If it's odd and greater than 1, it'll do one of these. So those are the basic shapes you can get. So if it's odd, it has to create a change of sign. So we have to go from one side to the other. If it's 1, it just goes straight through. If it's greater than 1, it will create a tangent point at the x-axis. So a tangent point means that it tangents it. It goes, for an instant, it goes flat. So even this one, for an instant, it goes flat. So as long as the multiplicity is greater than 1 at the x-axis, at the root, it will go flat for a second. We say it tangents the x-axis. So if the multiplicity is 1, it's going to look like that. If it's even, it's going to do a U-turn. If it's odd, it's going to do a horizontal stationary point like this one, or a saddle point, sometimes a terrace point, so a few different names. Horizontal point of tangency. So pull off the degree, find out where your roots are, look at the multiplicity of the roots, figure out what your lead coefficient is, figure out what your y-axis intercept is, do a little sketch. It's a little harder to see where the turning point is here. We're going to have a turning point there. We don't have the skills on this course to really see what the x value of that one is. That comes from the derivative. But because this is 2 and this is 1, it's going to be a little closer to the 2 than to the 1. Don't assume it's at the y-intercept. Yeah, that's about it. Consider the end behavior and you can sketch it. Let's see if we can sketch this one quicker now. Have a go at sketching this one. We pause the video a moment. Okay, so let's have a look. What's the degree of f? 3. This is a third degree polynomial. What is the lead coefficient? -1. What's the y-intercept? 0. It's not 12. What is the Sorry, I was just thinking something. What are the zeros?
0, -3, 4.
0, -3, 4.
Always try and list your zeros from smallest to largest. It's just neat. As x goes towards in positive infinity, what does y do? It goes towards negative infinity. Why?
Because it's an odd.
Because it's a -1 at the start. It's a negative x at the start.
You need two things. The degree is odd, and the lead coefficient is negative. Yeah. So it's going to go in this direction. So then let's plot these, -3, 0, and 4. So we want to start here, come down like that, go down like this, go down like that.
But how do you know at which point it starts to turn back around to get to the other two?
You don't necessarily, it's a sketch, so don't plot it.
Okay.
Don't put a scale, just mark the information that you do know.
How would one figure it out?
If you were wanting to find those points, you have to differentiate, expand the bracket, differentiate the function, set the derivative equal to 0, solve, get the x value, put it back into the function, get the y values.
Okay.
All right, let's have a go at this one. All right, let's have a look at the answer. Here is the question. It says suggest, so you can use any lead coefficient you want. I'm gonna generalize it a little bit more. So we're gonna get f of x is equal to k bracket x plus 2 with a multiplicity of 2 bracket x minus 3, where k is less than 0. Would that work?
Yes.
No,
anything negative.
No, but k is always less than 0.
If k is positive, then the leading coefficient will be negative, and we can see that the y-intercept is
K is not positive, it's negative.
Yeah, that's what I said. If it's positive, then the y-intercept will be on the negative side.
But also, I'm taking it from the end of it. Could there be other answers than this one?
Well, yeah. Could it be U4? Could it be X plus 2?
Hold on, let me shout at people. Come here, quiet. It does matter, yeah, because you need the turning point to be on the -2. So it's the x plus 2 that has to have a multiplicity that is even. You don't. If you would get a similar looking graph with a multiplicity of 4, it would look very similar. Not quite the same. You'd start to notice. I can see how even this curvature and this curvature is the same. So I do know that this one's a third degree function. If it was a 4 here, the curvature here would be bigger than the curvature there. But I wouldn't mark it wrong with a 4. But typically the question would say of smallest degree. You often use the phrase of least degree. Suggest a polynomial function of least degree for the given function. And then stops any of that. This one can't be greater than 1. This one has to be 1 because of the shape there. All right, that's it. Have a go at the questions from the worksheet while I mark.